Barely nights. We barely nights. Yo, check it. Yo, check it. Let's see that our audio is good. Yo, check it. Good. Yo, check it. We have very nice audio. Very nice. All right. All right. Let's see what's going on in the universe. Is there still a universe? Physics. What? Physics completed its mate nearly. Oh yeah, I wanted to watch. Okay. I wanted to watch the guy with
the Nobel Prize in
the
Physics.
guy with the stash.
Okay, so this video is.
There's a video, very nice video. Where's the
You've
guy
probably
with the
seen a
stash? The guy with the stash.
Imagine an idea so
The guy
the
with
one
the
you talk about, we'll just
stash.
draw it as an arrow up or down with a question mark next to it.
No. This guy. This guy. Let's see what he
The
says.
winners of the 2022 Nobel Prize in Physics were recently announced, and the awardees, Alan Aspect, John F. Clauser, and Anton Zeilinger, basically won it for proving.
He's actually a musician. He basically quit making physics and went full-time musician. So this music should be his, but I don't think it's his.
Proving Albert Einstein wrong.
It probably is.
Hello there, my name's Parth. Let's talk about the
Is your first name Parth or full name Parth? Last name, middle name? What kind of a name is that?
2022 Nobel Prize in Physics. According to nobelprize.org,
I think he's gay. The stash, the lighting. I think he's gay. The hair. Not judging, just my gaydar. I have a very strong gaydar. The glasses. I don't know. The Batman? I don't know.
the three physicists that won the 2022 prize were given it for experiments with entangled photons, establishing the violation of Bell inequalities, and pioneering quantum information science. In this video, I want to talk a little bit about what some of that
Good. At least no more music. That's good.
actually means. Let's begin by understanding that quantum mechanics is a physics theory developed to understand the behavior of very small things in our universe, and by extension,
Let me just make sure the audio is good.
developed to understand the behavior
Yes.
bigger things that are made up of those smaller things. For example, theory developed to understand the behavior of very small things in our universe, and by extension, bigger things that are made up of those smaller things. For example, we commonly use quantum mechanics to understand how particles, such as electrons, protons, and neutrons,
They're not particles. You're welcome. Roll the credits. We're done.
interact with each other to make up atoms, which of course make up all of the stuff around us. The thing with quantum mechanics, though, is that it often goes against common sense, and also against all the theories of physics that came before.
So does every magic trick ever. Yeah. It's just a magic trick. You have to figure it out. That's all.
For it, collectively known as classical physics. But if that's the case, why do we keep quantum mechanics around? With quantum mechanics, though, is that it often goes against common sense, and also against
I've always, I don't know, always, most times I've figured it out. And it's just a magic trick. It's just a misunderstanding. It's like gravity used to mystify until Newton and Einstein. The more we understand it, the less mystic it is. So you you're mystified by black magic, but it's just magic. It's just a trick. You have to figure it out.
All the theories of physics that came before it, collectively known as... The thing with quantum mechanics, though, is that it often goes against common sense, and also against all the theories of physics that came before it, collectively known as classical physics. But if that's the case, why do we keep quantum mechanics around? Well, simply because it works. It's excellent at predicting how any system that we're studying should behave when we do experiments on it. In fact, quantum mechanics is better at predicting how the systems that we study should behave than any of the theories that came before it. So far, all the experiments we've done firmly point to quantum mechanics being a correct explanation.
I don't know what that means. They all keep repeating. I never see what they're talking about. I mean, if they're talking about non-weirdness, what they call weirdness, the non-weird aspect, yeah. I mean, if you completely ignore, let's say, superposition and entanglement, the only weird thing is the collapse of the wave. Let's ignore that for now. So, yeah, I mean, quantum mechanics is extremely accurate. I mean, it gives us the atomic bomb. But you don't need to know entanglement to build an atomic bomb. You don't need to know superposition to build an atomic bomb. You don't need to know about the collapse of a wave to build an atomic bomb. Yeah, and the atomic bomb is an accurate science. So, yeah, I agree. But they mix the things that are still they don't understand. They mix it with the rest of it. They say, oh, quantum mechanics, it gives us the most amazing predictions. And part of quantum mechanics is entanglement. Therefore, entanglement is absolutely true. I mean, entanglement is true, but the question is what's causing it. Anyway, we're not going to go there now. Let's listen to this. Let's listen to him.
Of the phenomena that we observe. But what exactly before it? So far, all the experiments we've done firmly point to quantum mechanics being a correct explanation of the phenomena that we observe. But what exactly are some of the problems with quantum mechanics? Why does it seemingly go against common sense, and what does this actually mean? Well, to understand this, let's first imagine that we want to study the behavior of a tiny particle known as an electron. Electrons are one of the particles that we saw earlier making up atoms. But in this case, we want to simply study how a single electron behaves moving through, say, empty space, just to make things simple for now. Using the old theories of classical physics, we could say that if we measured the particle's speed and position at some point in time, then we could use some simple equations to predict where the particle would be at some later point in time. Really simply, if our electron was here at x is equal to 0 at the beginning, and it was moving at a speed of 3 units per second, then we could predict that 1 second later we'd find it at x is equal to 3 because it was moving towards the right. And assuming we had accounted for all the things our electron could interact with, which in this case is of course nothing, then our prediction would be correct every time we did this exact experiment, measuring an electron at a time 1 second after it was found at x is equal to 0 with a speed of 3 units per second to the right. Fairly common sense, right? Now, with quantum mechanics, every system that we study must be assigned a wave function. This wave function
that's nonsense. That's, you can do whatever you want. Nothing must be done. That is absolute and utter nonsense. Absolute nonsense. Absolute nonsense. This is spreading disinformation. What does that even mean? I don't even know what that means. We had evidence that the electron is waving and the photon is waving. We have evidence that things wave. To come from that and say every quantum system you need to assign a wave function. I mean, you can, if you, but it's like I have a string. I have a string lying on my table. Let's assign a wave function to the string. I mean, you can analyze a string using wave mechanics. You can. You don't have to. If I drop a string from a building and it falls down, do I need to use the wave function to analyze the behavior of the string? I could if I want. I don't have to. Let's see.
Basically contains all of the information that we can know about our
I don't know what that means. I honestly don't know what that means. I don't know what that means. I don't know what that means. I don't know. Please explain to me. Where do you get this from? What is that thing? You keep talking about the wave function. The wave function is like, you might as well worship Jesus.
system. Specifically, it tells us the likelihood or probability of finding our particle, in this case, at different points in space.
It's not a particle. It happens to be actually a wave. It's not that every quantum system you need to assign a wave function to it. The electron, we have evidence that it behaves like a wave. So you can analyze the electron as a wave. Since we notice that it behaves like a wave, it goes through two slits at the same time. Only waves do that.
If we were to do a measurement in order to find out where it is, just like we did with classical physics earlier. So let's say, for argument's sake, that for our system here, the wave function looked like this. In quantum...
Okay, I don't know what he's talking about. I don't know. I don't know where he's going. And how is this related to the 22 quantum entanglement? I don't know.
Mechanics. If we take the wave function...
I don't think anyone else talked about the wave function in regards to the 22 Nobel Prize.
And we square it, technically taking its square modulus, then this gives us the probability of finding our particle at different positions.
Why? Why is that so? Please explain. What's the mechanics behind that? Why do you say that? What's your evidence for that?
In space. In this particular case, because the wave function squared has a high value at this point in space, we're more likely to find our particle here when we do our measurement. And we're less likely...
Is that not also true for any classical object?
...to find it here, for example, where the value of wave function squared is smaller. And this is where all the quantum weirdness comes in. Quantum mechanics is a probabilistic theory. All we can find out is the probability of getting a particular experimental result before we actually make the measurement. Once we make the measurement, of course...
Isn't that true for classical physics as well?
We've got the data, we know where it is, there or thereabouts. But before the experiment, we can only predict the probabilities with which we'll find it.
Isn't that exactly the same for any experiment ever?
In different locations. Whereas in classical physics, we could predict exactly what the outcome of the...
I don't know what that means. I don't know what exactly means. There's always error bars. Always.
...experiment would be before we did the experiment, provided we had enough data about the system.
Provided. Schmovided, govided. No! What are you talking about? There's no such thing. What do you mean provided? What is that? I don't know what that means.
To put it another way, in classical physics, if we did the exact same
Why don't you give an actual example? This is total nonsense.
Experiment over and over, we'd get the same result over and over.
No, you wouldn't. You'd get error bars. You'd get the same result within error bars over and over.
But in quantum mechanics, supposedly, doing exactly the...
What do you mean supposedly?
...same experiment would give us different results each time.
Well, give us an example. What are you talking about?
This somewhat goes against common sense.
No, there's nothing goes against. I don't know what you're talking about. Why? I've been listening to you for years. What are you talking about? I still don't know.
It's because we usually inherently believe that doing the same thing over and over again, the exact same...
I don't believe anything. What are you talking? I don't know what you're talking about. I don't know what you're talking about.
...thing over and over again should give us the same result each time.
I don't know what you're talking about.
In other words, then, this
is just assertion. He might be right. He might be 1,000% correct. I have no idea what he's talking about.
Idea goes against our liking for determinism.
What are you talking? What are you talking about?
Or cause and effect.
What are you talking about?
which is the idea that if we know everything we are allowed to know about the system, then we can predict exactly.
Yeah, but you never know everything about any system. You never know. How can you know? How? How can you know?
Or with 100% certainty.
There's no such thing as 100% certainty. There's always uncertainties. What are you talking about?
How it should behave. Again, presuming we know the rules that it must follow. Now,
yeah. Well, what if you don't know the rules? For example, you don't know the rules. There's all sorts of uncertainties.
Very quickly as an aside, if we want to calculate what the wave function actually looks like for any given system, then we plug in all the information about it, such as what's in the system and what's surrounding it, into an equation known as the Schrödinger equation. And then
Poor Schrödinger.
we can solve the Schrödinger equation to find the wave function. All of this is not super important to us right now, so please check out this video up here.
Yeah, no one talks about the wave function in reference to the 22 Nobel Prize and Bell's theorem, whatever, inequality.
Here, also linked in the description, if you want to find out more about the Schrödinger equation and about wave functions.
He makes it so mystical. It's not even relevant. Not even relevant.
But let's now come back to this idea of quantum mechanics giving us probabilities, and also the idea that the exact same experiment being conducted over and over could supposedly give us different possible measurement results, with us not knowing which result we would get in any particular experiment before we actually did it.
Just like every other experiment in the history of ever. You're welcome. Roll the credits. We're done. What are you talking about?
Einstein hated this idea.
I hate what you're saying. What do you mean this idea? What are you talking about? What? If I only understood what you're talking about. I keep listening to all these YouTubers and all these professors. What are you talking about? Please, if I only understood. It's like a cult. What are you talking about? Then there's no access to these people.
He, along with Podolsky and Rosen, wrote a paper that used the ideas of quantum mechanics to try and find a logical inconsistency. In this
Logical inconsistency in what?
paper, they studied a theoretical system made up of two entangled particles. These particles would be generated from a single source usually, and then separated really far away from each other. But crucially, we could say something about these two particles based on what we knew about the source, or what came before the production of these two particles. For example, if these particles were made by splitting a bigger particle, and that bigger particle initially had some amount of linear momentum, what we normally just know as momentum in high school physics, then the linear momentum would have to be shared between the two particles that were produced, because of the principle of conservation of linear momentum. Momentum cannot magically disappear from a system, neither can it be magically gained by a system. The amount of momentum in a system must stay the same if the system is not interacting with anything outside of itself. Now, what we've talked about so far is basically fine in both classical and quantum mechanics. And linear momentum is all well and good, but a more commonly used example is some sort of angular momentum, such as spin. Now, I've made videos discussing what spin is previously on this channel, so check them out up here. One of them is linked there, and also in the description box.
I've heard all your videos. I've heard everyone's video about spin. I still don't know what spin is. You're welcome.
If you're interested. Basically, though, spin is a type of angular momentum, which is another conserved quantity.
Some people say it is, some people it's definitely not. I don't know. I don't know.
Imagine
it seems to be a conserved quantity.
Particle we started with.
They say it's intrinsic. They say that the electron has intrinsic spin. Intrinsic angular momentum? All right.
No spin.
It can only spin in a certain amount.
No angular momentum. So the particles that come from it also must have overall zero angular momentum.
Okay, so the parent had zero spin, so the daughter particles should add up to zero spin.
Imagine the particle we started with had no spin, no angular momentum. So the particles that come from it also must have, overall, zero angular momentum. This could be the case if both particles had zero angular momentum themselves, or if they split into other kinds of particles that had some amount of angular momentum each, but they cancelled each other out because they had the same amount acting in opposite directions. The overall result of this is that before the system had zero angular momentum, and after it still has zero angular momentum. The interesting thing, though, is when these particles have angular momentum and we try to measure what directions each of those angular momenta is in. For two particles separated by very large distances, we could simply work out what angular momentum both had by just measuring one of them. For example, if we measured this one and its angular momentum acted in this direction, then we immediately know that the other one has angular momentum acting in this direction. Remember, the net angular momentum has to be zero. And we haven't even necessarily had to make a measurement on the second particle. Now, quantum mechanics said that before we made a measurement, the system was not in any particular angular momentum state.
That's nonsense. That's obviously nonsense. This is the crazy superposition that they believe in. That the system is not in any state until you measure it. When you measure it, the system suddenly collapses the wave function and it gains a state. Nonsense. Obviously, that's nonsense. That's non-realism. So the moon doesn't exist when I don't observe it. This is what these people believe. The cat is both dead and alive as long as I don't observe it. What if this... So what if I observe the cat, but then somebody else walks in, he didn't yet observe the cat, so to him, the cat is both dead and alive, according to these people. So the cat is, to me, I discovered that the cat is alive, but the other person who just walked into the room, they don't know yet, so to them, the cat is both dead and alive. Literally, even though I know the cat is alive, to the other person who doesn't know, who didn't do the measurement yet. But they would say, no, I already did the measure. So what if I did the measurement? What is that? So what? What if I'm in a box? Let's say I'm in a box and the other person comes in and didn't open my box. So as far as they're concerned, I'm in a superposition of both knowing the cat. Anyway, it's complete nonsense. This is utter nonsense, obviously.
Making the measurement actually caused its wave
No, measurements don't cause anything. You're welcome. Roll the credits. Bye.
function to collapse into a particular
collapse. Oh my god.
State. Because remember, the same measurement could give different measurement results, and it was said that the act of measuring caused the wave function to...
Yeah, you said that. That's an assertion. You want to live your life like a mad person? Enjoy. I don't care. I don't believe that, obviously. You don't believe that, obviously.
to collapse into the particular
This is literal disinformation.
state that was measured. Whereas classical physics said that the system was already in one state and we just didn't know which one it was
Yeah, it's the same for an electron, for all the particles. It's just the same. You're welcome. Roll the credits.
in until we measured it. The interesting thing about the quantum argument, though, was centered on the following question. How would the second particle know that a measurement had been made on the first particle? And
Yeah, it wouldn't. It wouldn't. This is such nonsense.
what state it needed to collapse into,
Oh my god.
especially with particles separated by large distances.
Yeah.
It needed to know instantaneously
Instantaneously violating a little bit of Einstein's relativity.
what state to collapse into, so angular momentum would be conserved for all points in time. But then this defied a concept known as locality.
Locality means you cannot violate Einstein's relativity.
The idea that no information could travel between 2 points faster than light could travel between them, since light is supposedly the fastest traveling thing in the universe. But here we see that the quantum system would need to communicate instantaneously.
No, it would not need to communicate. I've written the code. You don't need to communicate. They could have had this knowledge, or the flip of the coin of the decision of the measurement is built in upon creation, and they share this hidden variable. So they're always correlated. They always give correlated measurements.
As soon as the measurement happened, which is
Oh my God. They already know each other's measurement results from the instant of creation. They don't need to wait for the time of the measurement. There's a hidden variable. You're welcome. Roll the credits.
Then light can travel between these two particles, and even more so when they're separated large distances. However, classical physics was saying, well, the particles are already in this state.
Yeah, that should settle it. That in itself should settle it. These people,
So there was no communication between the particles.
Yeah, there's no communication. And even if there were communication, how can a particle change its own measurement? How? That's ridiculous.
When the measurement was
just another problem. Even if a particle knew, oh, the other one just did that, even though they could both be at the same time. But fine, he would. How would he change the outcome of the measurement? How can a particle change the outcome of a measurement? These people.
Made. It's just that we found out what state the particles were in. We gained information.
Yeah, it's the same. It's the same. It has to be the same. Oh my God.
By making the measurement. For slightly unrelated reasons, this classical argument could be disproved. This video is long enough already, so I won't go into that here, but once again, there's some research.
Wait, everything you said could be disproved, and I'm wasting my time talking to you. Why am I talking to you? Who is in charge here?
Sources in the description box down below if you want to find out more about it. But the point is that according to
the point is, even though everything I'm saying is not necessarily correct. Let's see. Oh my, I'm not gonna read. Oh my, are you out of your mind? Merch, buy, give me money. Give me money. I am smart. Quantum entanglement is weird. Give me money. Give me money. That's it. That's like in two sentences. The Nobel Prize around the time quantum mechanics and classical physics. If you get enough information in quantum mechanics, however, we can get all of this goes against common sense. Einstein, Podolsky, they reasoned that therefore they showed that they suggested that hidden variables which we would never have access to were ingrained within the particles and told the particle what state to be in at any time and position. No, just the outcome of the measurement. This way we would just catch the particle, whatever. Doing an experiment to explain the difference between these two hypotheses, hidden variables versus quantum, was difficult until John Bell came along and showed that correlations between results of multiple such measurements were expected to be different between the hidden variables. No, that's incorrect. That's obviously incorrect. Everything John Bell said is incorrect. I proved it. You're welcome. Roll the credits. This is where our Nobel Prize winners come in. They each worked on improving Bell's. The Bell's theorem is incorrect. I can prove it. I've proved it. Let's show it again for the 1 trillionth time. Quantum entanglement. Where's the paper? Yeah, I guess this is enough. You just need this. Oh, not this, the other one. This, that, and the other. Is this the one? Quantum is still utter nonsense. The first one is after all, and the second one is still utter nonsense. Yeah, this is the one. Here it is. Here's the code. You can look at the code, and 100% correlation. Exactly 100% correlation. We measure in the same direction, but we create them in opposite direction. They share a flip of a coin. Here is their each measure function. There's no spooky telepathy at a distance, and it's 100% correlated. It's not 99%. So everything Bell said is incorrect. You're welcome. Roll the credits. Have a great rest of your life. Unbelievable. Unbelievable. It could be experimentally verified. Did the experiment close loopholes and further developed quantum information theories to study ideas like quantum teleportation? Exclamation. Yeah, they're just wasting everybody's time and money. You're welcome. You're welcome, humanity, for me stopping waste of money nonsense. Thanks for watching, and please buy it. Please give me money. Give me money. Give me money. I want money. Money. Unbelievable. Unbelievable. The sad state of affairs. Hi, friends. Thanks so much 2 years ago for watching and for your support. Give me money. Please check out my quantum mechanics playlist here for some other videos on this. Yeah. This makes me sad. Educational tubers are always overshadowed by things that don't matter in a few weeks. How are you under 200K subs? Jesus Christ. This was brilliant. Oh, genius, genius. I'm such a genius, a genius. How many? Anyway, I don't care. Let's continue watching this nonsense.
Quantum mechanics, in order for us to be able to do this experiment and for quantum mechanics to be correct, we would have to break determinism from earlier as well as locality.
Yeah, so obviously everything you said is incorrect. You're welcome. Roll the credits.
So why did Einstein dislike this so much? Why did he hate the probabilistic?
Because you don't need to break all of not just physics, reality, logic. You don't need to break the universe. You can just explain it with a hidden variable. You don't need anything else. So of course, what do you mean? He hated breaking the universe because he could explain it with a simple hidden variable. Why wouldn't he prefer to bring more money into the physics community and claim that it's magic, it's telepathy, it's teleportation, it's telekinesis? Einstein, he's so weird. He could have made much more money. That's what you're asking. This is nonsense. Here is the answer. You're welcome. You're welcome. Here is the answer. What else do you want to know? Tell me, what else do you want to know? Please tell me. This is it. There's nothing else. There's nothing else. This is it. What else do you want to know? Tell me what you want to know. Tell me.
Nature of quantum mechanics. Well, it's because both classical physics as well as his two theories of relativity, which had only recently been super successful at explaining the universe on a large scale, relied on the ideas of determinism and locality. These two concepts formed the foundation of his theories, so he wanted quantum mechanics to also be deterministic and local, which is why he thought that the then current theory of quantum mechanics was incomplete without these two foundations.
Well, the hidden variable completes it. You're welcome. Roll the credits.
And he, alongside Podolsky and Rosen, suggested a rather clever way in which quantum mechanics might be deterministic and local after all. Einstein,
What do you mean might be? With a hidden variable.
Podolsky and Rosen, or EPR for short, suggested that there may have been some hidden variables that we could
Here it is. Here is the hidden variable. That's all you need. You're welcome. Roll the credits.
never have access to, which basically
Lambda is the hidden variable? I didn't know that.
determined deterministically.
Exactly. That's what I did. Exactly. It's so simple. Switch to anti-clockwise particle 1. I mean, not exactly. I mean, it's just a random variable that they share that predetermines the outcome or predetermines the influence. I mean, if you want to go into the details, so you create a randomness influence, and then you still need to determine, right? I use the sine squared of the delta angle to determine, to determine the random influence, right? This is just the randomness. You cannot just take the randomness and randomize always the same, because that's not what ends up happening, and that wouldn't make any sense. The more they point in the same direction, the measurement is in the same direction or in opposite, measuring equipment. The more the measuring apparatus is either correlated or anti-correlated, the more this has, the more randomness, the less randomness goes to zero. So you need randomness to go to zero at 0 degrees and 180 degrees. And if you want, there is a paper, software simulation. Here is the paper. You're welcome. Here you can read the paper. Here's the abstract. Here is an example of the results. I've run it many times. It's always 100% correlated. Here is the ChatGPT prompt to write the code. You're welcome. Here is ChatGPT's response. You're welcome. Here is ChatGPT's code. I didn't write a line of code. I don't care. I'm not here to write code. And here's ChatGPT's explanation of key parts. Especially, you might want to read the probability. Everybody's so intrigued by the cosine squared. ChatGPT says, which is common in entanglement experiments. The randomness influence is sine squared, and because we want to achieve at 0, which is highest at 90, and 0 at 0 and 180, the randomness influence. Is there anything else? No, that's it. You're welcome. Enjoy the paper. You have the link at the top. I don't know what else to say. I don't know what else to say, you know. Everything is really straightforward. It's I'm sorry for boring everyone, but you know, we need to keep this up. 1 second, I have a message. 1 second.
What state the system should be found in at any given time, independently of any measurement.
The direction in which we measure the spin, of course, also makes a difference, but will keep things simple or not. Anyway, my code explains it.
That we were to do.
ChatGPT's code explains it. My prompt to ChatGPT explains it. The paper, everything is explained. It's really straightforward. Let me move this maybe all the way to here, because I keep switching between these two and I get lost with all the other things. This should also be here. Maybe X should also be here. All right. Very nice. What else do we want? Yeah, this guy.
On it. We, as measurers, would not know what the hidden variables were, or how they worked, or how to get to them, but the system wouldn't randomly collapse into a state because we did our measurement on it. The hidden variable would cause the system to just continuously change.
He's explaining basically perfectly how it would work, but for some reason, it's inequality. It's not equal. It's not as strong. Why is it not as strong? Tell me, why is it not as strong? How can you strengthen this? They are exactly 100% correlated. How can you strengthen this correlate? Tell me how you can strengthen the correlation. Tell me. I'm curious. I need to finish because somebody might be visiting me soon.
Change over time, however it worked, and we would just simply happen to catch it in a particular state when we measured. This system was deterministic because there was information that determined how the system behaved, even if we didn't necessarily have access to it. And it was local, because there was no faster-than-light communication when the measurement was made. The other particle not being measured was continuously changing, and we just gained information about it. The key was that the randomness that quantum mechanics brought was hidden away in the hidden variable. The problem, though, was that designing a real experiment that could tell the difference between these two possible theories, randomly collapsing quantum systems and local deterministic hidden variable systems, was really difficult. However, eventually a scientist named John Bell showed that there was some forms of correlation between the results of multiple measurements on many versions of the same type of system, and the amounts of expected correlations were different between the quantum model and...
Why would it be different? Why would it be different? There is exactly 100% correlation with the hidden variable. Why would it? What are you talking about? Please explain to me. Why would it be different? Why would it be different? Why would it be different?
And the hidden variable model. He showed this using an inequality known as Bell's inequality. Now, this inequality really deserves a video of its own in order to do it justice. I don't want to rush it by shoving it towards the end of this video.
Clauser, Nobel Prize winner. This is actually a more realistic version called the CHSH inequality. E, I guess the expectation, AB minus plus, blah, 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 blah. I don't care.
So please let me know if you'd like to see a video on Bell's inequality. But this, finally, is where our Nobel Prize winners come into the picture. John F. Clauser took the Bell inequalities and developed them until a real physical experiment could be done to show which of the theories was more likely to be correct. Alan Aspect further improved on this by closing some loopholes that could have tainted the results. And Anton Zeilinger took all of this further and worked on entangled states to understand quantum phenomena such as quantum teleportation. Pretty cool, right? Through the work of these three scientists.
Yeah, pretty cool. Pretty cool that it's utter nonsense.
As well as others like John Bell, we saw experimentally, over and over, that the predictions for the correlations made by the hidden variable model were violated, and the predictions made by the random collapse quantum mechanical model were more closely matched in our experimental results. In essence, these three scientists won the Nobel Prize this year.
This is such nonsense. This is 100% correlated. The hidden variable is 100% correlated. You cannot tell me that it's less strong than the quantum and the whatever, the teleportation, the telepathy.
For proving Einstein comprehensively wrong. And with all of that being said, I'm going to
Einstein was not proven wrong.
finish up here. Thank you so much for watching. If you enjoyed this video, then please hit the thumbs up button, subscribe, and hit that bell button for more
Thumbs down. Terrible video. Atrocious. Absolutely atrocious.
fun physics content. Please check out my merch, also linked in the description below.
Give me money! Give me money! Give me money! I want money! I want money because quantum entanglement and the wave function. Give me money! Money!
It features a quantum dice design based on a famous quote that Einstein made when talking about quantum mechanics and how he hated the probabilistic nature of it. And finally, a huge thanks to all of my Giga patrons and all of the others.
I don't know what they mean by he hated the probabilistic nature of it. I don't hate the probabilistic nature of it. Why did he hate it? I don't know. I don't know what they're talking about.
On my Patreon page, if you'd like to support me on there, that's also
Give me money! Money!
in the description box below. Thank you so much for watching once again, and I will see you very
Thank you for giving me money! I want money! Yeah. All right. 1 second. Give me money. I want money. Money. All right. Let me modify parth. So today we debunk this. I don't want to call anyone names anymore. It's too dangerous legally. Debunking. What's his name? Parth. We'll come back. It's too long. Okay, debunking Parth. What's his name? Parth G. Parth G. Copy. You can't copy text? Copy clean link? Copy link address, I guess? I don't know. Give me money! Give me money! Parth G. Oh, that's the name? Okay, whatever. Whatever. So debunking Parth G. It ends up being too long, so I don't know what to do. Nobel Prize in Physics. Maybe 21. Oh, that's way too long. I don't know what to do. I think we can maybe remove this. Still too long. Maybe I can remove this and this. What else? Still 10 characters too long, so let's remove this and this. Still 8 characters too long. Debunking. I don't know what else to do. I have to remove something from here. Proving Einstein. I don't know. Like he has a long title. Maybe Parth G. I think we can just say Parth G. Shut up. One second. So we need to say debunking. Debunking Parth G. And that's too long. Oh, we can say debunk. Debunk, and then it's perfect. Almost. I mean, debunk Parth G, and then the rest of it, we can add colon. Then it's perfect. Okay. Now let's give the link to Parth G. And I think that's enough. So debunk, Parth G, Nobel Prize in Physics 22, explained quantum entanglement, proving Einstein wrong. Perfect. All right. All right, everyone. All right, we're done. We're done with this guy. All right. I'll take a break and I'll see you later.